Welcome, 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 everybody. I'm back. Back at it. Been working in the background. Been doing some studying, but just not live. But we're back, we're at it. Had to get some house projects done. Had to make my coffee. I put like a flavored salt in this one this time. It's questionable. It's questionable at best, but it's like a healthy salt. It's good for you. Anywho, we're gonna warm up. We're gonna be no messing around today. Is the music too loud? Where are we at? Is the music too loud? Cheese and rice. It's been a while. Stand by. There, maybe something like that. Okay. Jesus is in the chat. Or is it Jesus? Music is good? Beautiful. All right, well, screw that then. Let's bring it back up to where it was. There we go. Jesus, welcome in, welcome in. We're gonna get right to it. I'm gonna do a little word of warm up. We're just gonna say hi. What's everybody been up to? Where you been? Where you coming in from? Where are you engineering right now in the world? Even if you're not an engineer, what are you up to? And we're gonna knock out our Wordle, and then we're gonna go right into a little problem that's been bugging me. Rigid diaphragm design, running those calculations. So there's a little snafu going on here, and I wanna kinda optimize it a little bit. So I got an Excel worksheet going, doing a rigid analysis, and then subsequently from that analysis, a drift analysis to determine if we have any irregularities in a building shape. So yeah, and it's just been a little finicky lately. So I've been tearing this thing apart, trying to rebuild it, and we're gonna get to the bottom of it today because it's just been freaking bugging me. So doing it live in front of everybody. Norwich, Connecticut, let's go, hey. Just south of where I'm from, in the Berkshires, Massachusetts. Love to see an East Coaster coming in, a New Englander. Get yourself a chowder and get comfy. Maybe a little dunks. If you know, you know. All right, let's get into it. I'm feeling, man, the sun came out today. It was like 35 in the morning here. It was cold. And then it warmed up. It was like 55 and sunny. It was freaking beautiful. Let's change up the beat a little bit here. So it was a little frosty. It was a little frosty. All right, it's workable. It's workable. No plows in this neck of the woods. Not like back home. Oh, what am I doing? But there are... But there are roads. Well, let's get an absolutely monumental one. Come on now. Not our best, not our best. I'm gonna swap. I'm just not feeling this particular one. Can we get a little... I'm gonna give this a shot, everybody. It just feels... All right, we'll roll with it. I try not to Try not to go directly to the lo-fi. But we'll jive with it. Hey, welcome everybody. I see you coming into the auditorium. Get in the seats. Get in your seats. Oh, by the way, if you notice, there's a couple reserve seats at the front. Little, new cushions, red velvet. You know what I'm talking about. The nice, what is that? Is that an oak finished handrails on the sides? Yes, it is. It's because those are subscribed engineers in Team Kestava over here on YouTube. And if you want one of those chairs, hey, hit that subscribe button. You don't have to if you don't want to. I get it. You can do like the old crappy chair. It's fine. It's got like the graffiti all over it with some great jokes on it, by the way. And the gut, you stick your hand under because you got to fold it and put it away. We all know what we're talking about here. And you stick your hand to the gum and you're just like, man, get me out of here. If you don't want that scenario, become a member. You don't have to do that. You just subscribe. Then you'll have your reserve seat. You'll have that front row center, and you'll always know that you can get in and the doors won't close on you. All right, there's my shameless plug. Let's get after it. All right, our R's and O's are all over the place, so we're thinking maybe let's switch it up, go to the end. Maybe like a one too much. Chored. I keep gravitating towards the P. I don't know why. Pull. I mean, unless we're getting real tricky here, we're starting with the O. Just for placement, what if we did, I know the L is, oh, that's not good. Come on now. Okay, let's go. I'm thinking way too far into it. Let's go a little more simple here. Let's go. Okay. That word doesn't correlate at all what I was thinking in my head, so just like, I just want to be super clear with that. So our R's way at the frickin' end here. You know, that sucks that So why did they flat? Oh, okay, because they're saying there's not two O's, but it also didn't tell me if this O wasn't here or not. I feel like that's cheating a little bit. Let's work with it though. Oh, we did pick up an... Okay. Oh, all right. So we should be able to lock this down. MI... Can't be an O. I'm just going to put an L for a hot sec here. O has to be here. I has to be here. Is that a word? No. Micro, mil, micro, 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 misro. Guys, it's right in front of you the whole time. Jeez. Okay, gotta wake up. Yeah, you in the front, wake up, come on, easy. It was a 5er, not great, not gonna lie. All right, what do we want to go to? Let's get... Get our Excel up. I'm thinking I want to break this down. I got to break it down by hand too anyway. So we're going to be doing hand calcs in conjunction to back up our spreadsheet. Something we always want to make sure that we're doing. Where do I want to go? Please hold just a moment. Please hold. All right. All right, let's get this over. All right. All Trying to think here. So I have a case that I'm working on. Let's head over. Alrighty. Oh. I'm going to be back and forth all over the place here. All right. Not gonna lie, I don't know what I was thinking almost drawing that. Let's just bring in the info so we can get to work here. Okay. All right, so that's our case. Stop chucking you all over the place. Okay. That's our walls, that's our stiffnesses, although I am going to update those stiffnesses. I was running some numbers yesterday, and I actually want to update them. Because what I'm actually going to do, the green, as you can see, is wood walls. For this analysis, because the others are masonry, their stiffnesses are so significantly less, I'm actually going to exclude them from the analysis because I'm running both I'm going to run both a rigid analysis and a flexible analysis, and then enveloping the procedure and then designing that way, because it's mass timber is what my design is. So technically mass timber is a semi-rigid diaphragm, so you'd have to, if you really wanted to get into it, you could through modeling, but instead I'm gonna kind of brute force it and just do both analyses and take the worst case design criteria from both analyses and design my walls and my diaphragms to make sure that they're adequate that way. So for the wood ones, the flexible analysis is going to by far create the worst case scenario for these wood walls, and then in the rigid analysis they're going to see very little load because they're significantly less stiff than a masonry shear wall. Wood walls are notoriously like the most flexible thing you could have, besides, like, I guess in terms of talking about shear walls, you know, talking about moment frames and stuff, that's where, okay, they could be comparable, but anywho. All right. Shoot, this is a previous saved version that I didn't want to be using. Yeah, this isn't what I want. Let me grab. Stand by. I'll be right back to you. I actually just need to grab the other file off of my thumb drive. I'm here with you in spirit. And we're back. Okay. All right, so this is the one I've updated. And I need to tweak a little more. All right. So, let's remind ourselves. And did I input my new stiffnesses to this? So, like I said, we're gonna go 0, and we're gonna go 0. Okay. I believe I did. These are updated. Okay, so this one is actually 747. This one. Actually, one of the things that we're going to look later at is converting. If we're getting some torsional regularities, let's convert this to masonry and see how that helps into trash. Hey, Frank, welcome in. Frank and Andy, welcome in, welcome in. Taking the PE March 1st. We got a month. Let's go. Let's go. Andy, same. What? Crazy. Hey, Frank, I appreciate the shout out. Let's go. I know I haven't posted PE specific practice problems in a while. During my SE studies and continued SE studies, they're a little more ramped up information than your typical PE, especially with it switching to computer-based, but I am glad that those are still helpful to people. Any practice problem you can get your hands on, like I said, man, it's helpful. Thanks for stopping in, brother. Huh, cool. All right. All right, and just like that, that's no longer going to be used. Megamind, welcome in. Seen you before. Roaming these halls. Alright. All right, so center of mass. Let's look in the, I'm gonna look in the FY direction. I guess I'm gonna stop kind of just like talking things out unless I'm really feeling it. But if someone is following along and you wanna know what I'm kind of thinking or the process I'm going through, just hit me up in the chat and I'll let you know. But I'm gonna kind of be mumbling here for a little bit. That's right. No, did my pen just die? Oh, there we go. We're live. Sorry. You know the sound. You know what time it is. All right, like this method is only good if you have two walls in a direction. So if I have multiple walls in a direction, how do I find my rigidity? Still, we'd be basically finding like your center of mass for a object. I want to say still like same equation. We basically need y bar and x bar for rigidity. So I think I could just use the same logic. Let's find out. Starting from a work point, that's going to be our big key here. It's going to be rigidity and a distance. Otherwise, it would be a mass and a distance when we're trying to find the center of mass. We're finding rigidity, center of rigidity, and distance. Okay. So we have 747. This is going to be so we're going to test it with 2 at, I don't know. In the spreadsheet I just did, I ran it at 1 kip per inch, excuse me. That way it just doesn't break the spreadsheet by doing 0. I have to look at that later, but okay. This one really doesn't matter because it's by 0, so, but regardless. All that over summation of rigidity. All right, we're in business here, so beautiful. That matches with what we had. Spot on, spot on. All right, so that's how, got it. Oh. Okay. This all makes sense. So we're taking this. We're taking the sum of our, in order to find the x component of our center of rigidity, we're taking the rigidities in the y direction, which we're denoting as big RY, and multiplying it by their x distance. Yes. Yep. We're summing those. and then we're dividing by our total sum of our rigidity in the y direction here. Good. And then we're just dividing. Excellent. Okay, so that's running smooth. This should be doing the same thing, only for our x components. Good. That yields our center rotation, which is great. All right. Good. That clears out. I almost want to do like a... Maybe we do this. Maybe we go across here, and we're gonna flag these with some green to know that like we've cleared through. So these are good. Basically, just what these are doing is converting and populating the stiffness for the direction based on the angle that we've given to say, hey, is it aligned in the y direction or the x direction? And then it's pulling that through from there once we've added the angle. This one is simplistic, so don't think that this could run everything under the sun. What I want this to do is just run cases where you have basically normal vertical lateral elements, 90 degrees, 180 degrees, or 0 degrees in this case, that in a box, in a rectangle. That's it. Anything else beyond that, we're going to be modeling stuff. We're going to be jumping into ETABS. So don't think that I'm trying to build cases where you can do weird angled walls or lateral elements in places. It's just, that's going to be a little too complex for right now. All right, quick second. I'm just gonna grab some water. Be right back. I suggest you do the same, everybody. Head to that water fountain, not all at once. Don't run. You can run in here, whatever. All right, be back in a second. All right, my question to myself before was, does the direction of the distance from the center of rotation to our lateral elements, does that need to be coordinated as like properly located with respect to the center of rigidity in terms of like positive, negative? Like if it's here, if I switch back, it's just talking out loud here. If our center of mass is here, center of rigidity is here, so with walls, so that means this is going, because this would be applied here, which is going to create torsion. I don't think that this value needs to be properly located, especially since I know our next equation, J, takes our littles and squares them. So that wouldn't matter if it was a negative value. But afterwards, our force per wall our direct shear doesn't matter. It's V X summation R. Okay. So by that value being positive or negative, will that influence things? Hey, Bruce, welcome in. You got a question? What's going on? Not sure you can. Hey, if you can't ask it all in the chat right now, go to my page under like information. Hook you up. And I do have my email listed there, so you can, people email me all the time if they have specific questions and stuff. Let's see what we got. Where we at? Oh, can I not see what you guys see because I'm... Huh. Well, crazy. Oh, I know it's there. It's in like the top ribbon when you go to my page. But yeah, hit me up, Hebrews. Oops, stay up here. Okay. I guess if this stayed positive, if we make sure that our torsion is designated directionally, that would that appropriately feed? Let's get into it. Let's figure it out with numbers. right, so I'm gonna start by absoluting all these. That's a good question. Unfortunately, right now, I need to focus on this, but that's a great little like PE question that I could get together, but I'm guessing that's gonna take too long for you. Single angle, bending. What load? Gosh dang it. Okay. Boom, and you're saying this thing is fully fixed, both ends. Then you're saying, I guess the load is gonna be pretty close to the inside. Not like so. Oh, not centroid. But it's fixed at both ends. At the mid-span and loaded through the shear center. Yeah, shear center, don't need to do like shear flow. Stand by, let me get this book. All right. Yes. So yeah, you're correct. The centroid is not the same as the shear center. Get you there. Okay. So the shear center can be... Sounds like the shear center is outside of the angle. Okay. Giovanni, welcome in. All right, wait. First 8 inches of deflection. At 60 pounds, I found it had fully rotated 45 degrees, but it was crude. I did it in real life. Oh, that's cool. The ends dangling off. Yeah, we're getting in a whole different rabbit hole here. What was your main question? So you did this in real life. That's pretty cool. You loaded it through the shear center. I don't think... I mean, I could be... I'd have to look into this, but... What do they say? The shear center... Hey, Giovanni, I appreciate it. Let's see. I'm going to do one quick search. I think an equal angle, so like a 4x4, 6x6, or an L 6x6, L 4x4. Your shear center is going to be at the intersection of the legs, is what I'm seeing here without running a calculation. What's that guy? Because that's how it's gonna. It's about the shear center is the point about which no rotation occurs as it's loaded torsionally. And I know you can calc that, but looks like equal angles. It's pretty straightforward. Or like that's already like, okay. So you were right. It's at the center of the vertical leg and the center of the horizontal leg where they converge on one another. So now where are we at? So hanging a load through the middle of the steel bar joist bottom chord. I thought we were doing an angle here. What would you talk about? Bar joists. That is the application, and define. Oh, define the friction force in the washer at hanger to prevent rotation of single angle so that they act together. Okay, so now you're getting into steel open whip joists. Bar joists. Yeah, I know what you're saying. You're taking me down this whole trip. I gotta focus here. What was your first question? Place at the midspan and loaded through. For what load P before it flips 45 degrees? I'd have to really get into that. I don't know off the top of my head. I'd have to noodle on that a bit. So overall, you're saying that someone's loading a bar joist. And you're trying to figure out how much load can hang from the bottom chord, one of the angles of the bottom chord of the open web joist. I think that sounds about right. I don't know why in application someone would hang something from that point. I would say you'd want to specify that anything being hung needs to be hung from the panel point of the open web joist, and then the connection is about the centroid of the open web joist bottom chord, so that it's concentrically loading the joist rather than having this eccentricity introduced and, as you said, putting some torsion into it. Yeah, I've done stuff like that before, but specifically getting into like loading specific points of bar joists and stuff, or open web joists is what I call them. And pretty much in practice we say don't do that and leave it at that. But getting into the nitty gritty of those products, I lean more heavily on the manufacturer to dictate what can and can't be done for their specific, truss girder, open web joist product. All right, Frank, what's going on? Where did those equations for bearing pressure come from? I actually, way back, I don't know if I did it on my channel. I think when I was like my earlier engineering days, I actually back calced how they derived those equations. If you break them apart, it's based on assuming the kern of whatever 1/6 and taking your resultant load. You can back calculate and derive that equation. I know it's like, duh, thanks. How did they make the equation? They derived it. But it's those bearing equations basically are calculating how much surface area we get to. Why am I talking? I got this in front of me. Like, basically, it's a function of, we remember, if we're in this state, we're looking good, but as we get more and more, and that's when, well, if we have no eccentricity, then it's just like this. So your P, and there is an M equals 0, so you don't have any moment, which means that your resultant is with an eccentricity is equal to 0. So that means your resultant is directly underneath your P, which means that you get an even distribution of bearing pressure. But if there is some amount of moment, it means that there will be some eccentricity, which then takes you to the next step. Oh, and that first bearing pressure is just P over A. The A being the surface area of your footing in contact with your grade. So that's a really simple equation. We basically, I mean, I know it's easy, but Q max, we just derived an equation. Hey, new subscriber. Eslam, welcome in. Oh, and it worked. Hey, check it. Check that out. Check that out. Little something to spice up the study sessions. What do we got there? I forget what even. Engineer subs. We're looking for 10. Let's see if we're gonna get there. But yeah, okay. Frank. So there's that one. Easy peasy. Then we apply some amount of moment, which gets us some eccentricity. Well, that's gonna push. I don't know why I'm doing that. That's gonna push our resultant R outside of our P, because we need to maintain equilibrium. And in order to maintain equilibrium, our equilibrium equations, Fx, Fy, and moment, well, Fx is just 0. Fy is gonna equal, is gonna be the equation P equals R, because P is the downward force, R is your resultant upward force. As long as those match one another, that's balanced. But then we have a moment here. So before, when we had our R balanced underneath our P, that worked for this equation. But now that we have a moment, we need to counteract that moment so that we have equilibrium, which means that we introduce, I don't say we, but an eccentricity is introduced, so your resultant shifts away from P, because that still provides equilibrium for Fy. P and R are still here, but now your R times E will equal M, and that now balances your moment equilibrium. So your system is balanced, and now it looks like this case here. And what that does is, depending on your kern, or how far this eccentricity is, you then can calculate this Q min value and this Q max value. And we remember that this whole thing is a summation of both of these equilibrium equations. So this one is just at the Fy portion, which is just P over A. Okay, that's easy. But then you have this going on, which is essentially your M over S equation. But what happens is, and then if you were to add those together, that gets you a resultant that looks like that. This equation, you could just say Q max is equal to P over A plus or minus M over S to get you Q min if you subtract, and Q max if you add. Case closed, right? We just derived another equation to use. But you're like, hey, that's not the one that I'm prescribed to use. You know, mine has the 1 minus E over 6 and blah, la, 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 la. And you're like, what the frick? Well, that's because if you play around with numbers, eventually, depending on your eccentricity, this equation breaks. If your eccentricity gets too large, this no longer works. And if you run the calculations, you'll realize it no longer works when your M over S component is greater than your P over A component. Both of these are stresses, remember? PSI. Actually, sorry. Most of the time they're PSF when you're comparing bearing pressure. PSF because it's pounds over over an area for both of them. The moment is a moment over cubic, but both boil down to a PSF. So when M over S is greater than P over A, correlates to this Kern limit. Because they correlate to an eccentricity, because as your eccentricity goes up, that also relates to how much that relates to your moment because of the equilibrium equations. So that's where smart people said, all right, well, this equation doesn't always work. When M over S is greater than P over A, it actually boils down to the equation that you know and love as P over BL, which is your area, and then I'm cowboying this, 1 minus E over 6 over L or something, I'm not quite sure. But that derived equation basically triggers and says, okay, we know that this works in all cases. It works when P over A is greater than M over S, and it also works when P over A, is less than M over S. So just use this frickin' thing all the time, then you don't have to worry about it. And then subsequently, it goes even further. They say, well, eventually, when your eccentricity is so bad, and your bearing pressure now looks something like this, because your resultant is way the heck over here, because you have a very large M. Now your eccentricity is popped way the frick out here, so your bearing pressure you don't get to utilize all of your footing for your calculation, because theoretically, this portion of footing is experiencing uplift. It's starting to rotate, and soil doesn't have any tensile capacity, as we know, so it just doesn't do anything. And in this extreme case, this equation, the first equation, this might not be right, so don't hold me to this one. No longer works. Well, when does it no longer work? It no longer works when you can no longer utilize your full footing area. So once Q min is less than 0, and when it's a negative number, you're flagged and oh shoot, I need to use the new equation for Q max, which is the 2P over 3 B E prime something. So, and then Capital Bricks just comes in here and he's like, dog, cumin, chef's kiss. In case you wanted to know. Appreciate it, cumin. Or appreciate it, Capital. All right. Frank, I hope you're still there. But if that just was a wild ride, just let me know. It's my bad, man. But we're gonna get back. Oh, I need those. We're gonna get back to it. That was a half-hour excursion that I don't know. I just don't know. But that was fun. All right. Nice and clean. Get the angle out of here. Not that I'm hating on the angle. I like that question too. That was cool. Oh, Frank is here. Let's go. Hey, no problem, Frank. I know it was fast. We were on the edge of our seats in the auditorium, but hopefully that made sense a little bit of those equations in particular. You can actually derive if you just sit down, play with the numbers, make a little, I don't know, a little Excel spreadsheet type of thing for that type of question, and just mess with the numbers and see as you mess with your axial load and your moment on a footing, and you mess with eccentricities, what starts to happen to all of these equations? And that's you'll come to the conclusion on how they derived these. Those ones are, in my opinion, kind of fun to derive, whereas there's other ones where it's like I'm not some mathematician wizard that I'm going to sit in an ivory tower for 15 years to get this thing derived and figured out. Are we in the jungle? All right, so we're back on it. So what I'm going to do that we just talked way far about, I'm going to switch this up and I'm going to make these values absolute and say that we don't care their direction. It does move things around, which I get scared about, but our polar moment's always going to be positive. Yes, and our polar moment's always positive because these things are squared, so that's fine. Let's absolute this as well. Flag these as yellow. Just say, hey, let's keep our eyes on you. Okay. All right, yeah, and I've split. I do want to do this. Oh, I'm forgetting how to do a sub. where's my sub number? Could just do this. Ah, no. Honeybee, welcome in. Check your R. Checking my rigidity. Frank's looking a little strut and tie analysis for deep concrete beams. Yeah, I got a great example on that. I've had to do those before in pile cap analysis that I've had to do in the past. But hell yeah. I guess I'm not gonna get... I'm not gonna get hung up. Driving me nuts. I'm forgetting how to go back to... Oh, this hurts. This is gonna be my battle right now, is freaking this. Control 1. Oh my god, that's right. Thank you for that. Yes. He's even got the hotkeys, or she. What an absolute freaking champ. We want our Y. We're gonna take that little number. Yes! MVP of the stream right now. All right, I'm gonna go in, do that. Oh, without a doubt, MVP. Although now I can say, what is that? What is it? It's 10. So it's not 10, I know that. What are you? Tell me. There we go. Yes. Okay. Okay. I don't, well, right now I've been keeping everything in X and Y components, but it doesn't matter. And they just zero out when it is denoted, when my angle is denoted to designate whether I have a wide direction vertical lateral element or an X direction oriented vertical lateral element. So this, is this absolutely needed right here? I guess let's hang on because this was still giving me troubles on direction of all my loads, so I'm gonna keep it split for now. Easier to keep it split than to undo it and then realize I wanted to have it split in the first place. So it's just doing one more step because now it's summing these, good and good, and then the sum of these should be, yes, should just be my polar moment. All right, we're rolling. That all looks good. Looks good to me. So I'm gonna flare these as happy. Happy? All right. I'm gonna go grab some water. I'll be right back. You do the same. All right, we back. Oh, what happened to the tunes? Who turned it off? Jose? Did you turn off the music? What's going on? Ah, there we go. Hey, Hebrews. Thanks for stopping in. See you next time. Hey, I appreciate that, man. Or woman. Later, later. Please don't tell me you saw this in the lateral exam. Remember, we can neither confirm nor deny what we saw on our engineering exams. You just got to remember that there's time limits, so there's only so much you are expected to do with the time that's given. Are they expecting you to need to build an entire spreadsheet to run some numbers and stuff? Probably not. Should you be knowing the inner workings of overall how this works if it was a really simple one and they spoon-fed you a ton of the info and you needed to fill in the blank or something? Probably. All right. This is where my accidental eccentricity comes in. I have that running. Let's keep it 0 for now. Okay. I'm gonna save this. So now this is the bread and butter of it. I have my 4 cases is what I'm running here. Basically my 4 cases. I know, but let's head back. My 4 cases are center of mass, center rigidity is Fy with eccentricity plus accidental. That's a case. Then I have Fy with eccentricity minus accidental. That's a case. Then I have Fx, eccentricity plus and minus for 2 more cases. For 4 cases total. So that's what's going on there. But before I had them broken out, or I had them all combined for how load was getting to my shear walls, but I want to actually break them up now into direct shear and torsional shear. Okay. So V direct we'll do, and then we'll do VT for torsional. It's going to be your torsion, and we know that torsion is equal to your shear times your eccentricity plus minus your accidental. That in there like that. Your V is simply these guys depending on the direction you're looking at. Okay. And again, it's important that the direction of your torsion, is it doing this or is it doing this, is important to distinguish which direction your torsional moment is actually loading your walls, which is going to affect your displacement, which is needed to calculate your irregularity checks. So I need to be I need to be aware of tracking as cases change. I keep drawing in front of my big head where center of mass is relative to my center of rigidity. Okay. Okay, so case 1. My shear in the X direction. That honkin' equation, that's both my direct and torsional shear added together already. So I need to break that out. And I'm doing E max for case 1 is E max for shear in the X direction, which is my EY. Yes, my offset is 0 because it's accidental. So my max eccentricity and my min eccentricity are the same values. So that's working. If I add my 5% like you should, yes. And then it adds it and subtracts it. Okay, good. I think that's running. But let's keep it simple for now so then we can complicate it later. This just broke down here because of my VLOOKUP. So all of this, that's what these numbers are down here. It's just helping me track my VLOOKUP when I'm pulling values from here. Okay. It's T. Okay, so this case is loading in the X direction. My eccentricity should be EY. Why am I making my E prime? Oh, I see. Yeah, that's fine. So it should be pulling EY. Oh, and then EY should be pulling EY. Yes, okay, so. Okay. So it's negative. It's because it's below my center of gravity. Hey, Nick. Well, you're just gonna barge in to the auditorium like that and throw out compliments like that. I appreciate it. I really do. I know it can be tough, right? Also, I can tell. Watching my videos after finish running problems for the night. You're at it. You're going after it, my man. I love it. Keep at it. You're gonna get where you need to be. And I appreciate the compliment. I really do. Hopefully I can keep evolving, keep enhancing the content that I create to help everybody out a little bit more. I think what I'm doing here right now is something that I'm experimenting with, doing kind of live problem troubleshooting type stuff. So I hope you guys like it. Or you can just kind of put it on in the background while you study what you need to study. It's not all about freaking me, right? Yeah, because I'm learning every step of the way, just like you guys are. So thanks for coming in. Thanks for the positive energy. I do appreciate everybody who subscribes, likes, and interacts with the channel. Overwhelmingly, I will say that it's positive, which is great because I think our field needs it. I think us as engineers in all the engineering industries beat ourselves up a lot. That's just kind of, I think, unfortunately, the engineering way sometimes, but I'm glad the community's been as positive as it has. Sounds good. Thanks for stopping in, Nick. Let's get after it. Hey, sweet dreams. Peace. See you in the auditorium next time. I got a little something going on here. It's exactly why I wanted why I wanted to spend more time and break up my direct shear and my torsional shear. Yes. Okay. Okay. But yeah, exactly. On B's in here, knows what's going on. Because what I need to make sure of is how I'm applying it directionally, torsionally. So if that's happening, they should be flipped. This one should be additive, which means that my absolutes should go away then. Oh, that didn't fix it though. Basil, welcome in. Will it be available for download? I don't know right now. I want to be cautious on like what, I can't guarantee everything. For the time being, I'm not going to do anything like that, but you can always come back and use this as a template and build something yourself that is similar. I need to just tell it based on if my wall is in relation to my rigidity, it means that it would be additive or it would subtract from it. Which is pretty straightforward, except it's like if I almost want those to be reversed. Because in reality, I guess if I have respect to distance from the wall itself to the rigidity. So in that case, this would be a negative value, which would get me what I want. And same here. So it would be the rigidity minus wall, rigidity minus wall. That flips. That still keeps our polar moment fine because we're squaring, so the negatives don't mean anything. But now, directionally wise, oh, it's because our, that's why at first. And our M max is, or M max is positive. Oh, shoot. Okay. Keep these good. That's actually the right way. It's, my eccentricity is good. And I want my EY actually. Oh, my E should be the distance from my, where are we? EX is, okay, it's going to create a negative, so, oh, EX should be negative. It should be the opposite. So it's negative when you do this minus. That's what I want to see. And then the opposite, I want to do that's positive with respect to my axes. I'm keeping everything with respect to my axes, so like down here, I'm taking the key thing here. Again, it's a simple spreadsheet that I'm trying to use here. It's limited. Like here, like the big thing is that this is my origin. So this whole thing is built off of that. And I have my x-axis and my y-axis, and anything moving up is positive. Anything moving down is negative. Same with here, plus, minus. That's where I'm playing around with these minuses, negatives, and positive values. And again, it's all, oh, no, you don't. It's all about saying, tracking my center of mass and my center of rigidity as they move around and as they swap and move with one another, as we mess around with your system. The negatives and positives need to keep up with that because it's going to change the direction of your torsion, which then changes the directions of torsional shear applied to your walls. Okay, let's go back. Max is this, and min is this. If I put some value in, shoot, so these gotta swap. Because it's, okay. Its offset isn't that much. Which now I think I can say negative and positive. Yes, and this one is gonna be positive and negative. Yes. This would be the same thing. Negative, positive. I flipped these. Yeah, I caught myself. I needed to start from the beginning is what I needed to do. Which is what I did here today. Good. That's all running nice now. You do like me. So you do like me speaking my thoughts while I'm doing this? Because I am happy to. I just don't want to drive anybody insane. But yeah, I think this is pretty cool. I do enjoy doing it. Okay. Good. All right, now we can build extract torsional, extract x torsional. We want the same thing only with y now. What you mean, do I not solve these problems? What you talk about? What you talk about? Okay. Wrong way. Okay. Vy. Hey, no problem. Can I just combine these? I feel like we could. So do this, plus all that, except we want GH. We shouldn't change anything unless this were to be 10, then it changes it, yeah. Good. Because again, I'm not going to run anything where I have vertical ladder elements at an angle. So this works to be able to combine them. Lock it, lock it. Lock it, lock it, lock it, lock it. Good, that works. What about this one? Yes, I do. Yeah, I'm at a structural firm. My torsional. Yeah, so I would, what I do here? Do the same thing. Yeah. We are literally gonna package this guy up. Package this guy up. Plus all of this. But we need to do some maintenance now. This needs to be H. And this needs to be K. So again, if that were to change, did that change? Yeah, it does. Barely, but it does. Yeah. Okay, good. All right. That's sum of directional. That's a sum of torsional. So now I actually don't need these cell blocks. Summation's going to be if this equals 90, then wait a minute. Oh, because they're combined now. Yes. This can just equal sum of these two. Okay. Okay, okay. Why you gotta be like that? Okay. Delete these. That X can go away now because it's just the total, which is beautiful. Cleaning it up a bit. Summation of Z. Okay. Yes. Yes. And then we could do an equals sum of all of these. And then we can put a type parameter or conditional formatting. What do I want to do here? I want to say this can I say if? Can I do if statements? No, I just want to say this equals if this, if that equals that, what's it gonna do? We can border it. No, we're just gonna fill it. We're gonna hit it with a very light green. Okay. Good. But if this were 1, nope, okay, good. So this one. Edit rule. Let's do that. Frick. Yo, anybody in the chat, do you know how to do like, if it's not equal to? So if that number does not equal this number, is it like, no. Equal dash? Does not equal? Then it's that? No. Anybody? Anybody? Equals that. Clint's on it. I love that, Clint. Thank you. Like I guess I could brute force it and say this, say okay. Say okay, and then I can add a new rule, do the same thing, and I can say equals this is greater than this, then we're red, then do that, say equals this less than this. Then we're that. So if this is 1, that's no good. If that's 100, that's no good. I guess I could do that. I just feel like that's a lot. Also, for anyone just coming in here, grab your seat in the auditorium. I am no Excel guru, so if you're stopping in here and you're like, dang, he's doing Excel, so I need to learn Excel from the master. I am not. I'm very basic here. I got a VLOOKUP in here, which is like, wah. Look at me. But besides that, yeah. So if you're cringing at stuff that I'm doing, well, I apologize. Let me know. Let me know some of your secrets, though. All right. I just wanted to add this as a stopping point to say, all right, we're good because we need to get summation of our forces equal to the force that was being applied on the structure anyway. If you're not, there's something is going wrong. Doesn't equal something, then do this. Exactly. You let me know, Clint. If you're ready, if you're locked and loaded at some point, I will go right back to that. Sum of base shear. Pretty much. In this case, it's the story shear in the direction that we're looking at. So in this case, the shear in the X direction. Oh, and I should manage these rules. Because what do I want to do here? Oh, good. They're already locked in. Oh, but this one. Okay, so there's not an option for that under conditional formats at the top. Let's see. New rule. Format all cells based on their values. Format only top or bottom ranked values. The values that are above or below average. Format only unique or duplicate values. Format only values, yes. Based on their values. So you're saying this guy. I've only ever created a formula. I've never used like the preset ones. If I do this, it changes to, oh my God. Jesus Christ, that's Jason Bourne. All right. Okay. Duplicate values. Format values above or below average. Format it if it's equal or above. So not that one. Format only cells that contain. Is it this one? I think it's this one, right? Because then we can go cell value. Not, equal to. Not equal to. Cell value? And then what do you do? This and do this, and then format it. So if it's not equal to that, then it's going to be red. Like that. Let's get rid of these. Do this, delete, delete, delete. So now if this is 1, oh my God, 100. Let's go. All right. All right, we're rolling. All I want to do is, I feel like this is a little harsh. Can we outline? Can I do a color outline? Do something like, oh, Jesus. There we go. No, let's do that. Outline it. The fill. Clear it. Border, font. Yeah. Okay. Oh, yeah. Let's go, team. Oh, the last thing with that. This is not equal to. It applies to that. Oh, shoot. Okay, B11's locked. Okay. Can I switch this? Can I do like a swath of these? This, comma, 1, 2, 1, 2, this. Why? Yes, so if this is 96, otherwise if this is 1, yes, okay. All right, Clint, appreciate it later. Yeah, that's a good point. I want to keep going with this, but I have to log off here, unfortunately. We've been here for a long time. I'm gonna pick this back up tomorrow and then be rolling some studying. I think we're close to the end here, which is nice. Now that I have this case figured out, like, I just need to convert it for this direction and then for those directions. And then that should be running smooth. And then I should be seeing what I want to see. So that is great news. So I'm going to hit save. Let's flag what we have done so far. This green. And we got to go from there. Yes. Yes. Okay. All right, team. Hey, before you go, like if you want to like, subscribe, because I could tell, I can freaking tell now. But hey, like I always say, you don't have to. So, but do it, but don't. But no. you know. If you want to join some engineers from around the world, collaborating together like you're seeing here, even if it's just a couple of us at a time, hey, make that connection, subscribe, get that reserved auditorium seat with the plush red seats and the oak, hard, nice, dark oak armrests. Sound nice? All right, then do it. Otherwise, I'll catch you tomorrow. I think it's going to be an earlier session. And yeah, let's wrap up this spreadsheet, and then let's keep going from there. Maybe we'll talk about it a little bit. We'll talk about rigid diaphragms, what it means, what's going on, what are these numbers that I'm plugging away at here at. But hey, appreciate all of you. Have a good night. Have a good morning, wherever you are in the world. Glad you stopped in. Peace.